Hello, welcome to the NPTEL online certification course on deep learning. So, we are discussing about the autoencoder or the different types of autoencoder. So, in the previous lecture, we have talked about what is known as sparse autoencoder, and as we have said that in case of autoencoder, we want the autoencoder to learn a compressed domain representation of the input data, or the autoencoder should learn salient features of the input data. It should not just memorize the input data. So, in case of sparse autoencoder, where we have assumed that the number of nodes in the hidden layer can be quite large, or in some cases it can even be larger than the number of nodes in the input layer or the output layer. But the compressed domain representation is enforced by enforcing some constant which we have said as sparsity constant. And what is sparsity constant? In sparsity constant, we have seen that what we have restricted is the average activation of a node or a neuron in the hidden layer. So, we have said that if say sigma j hat is the average activation of the jth node in the hidden layer, then this average activation should be constant, or it should be equal to some sparsity value, sparsity parameter, which is equal to rho, where rho can be say 0.1, 0.01, 0.2 and so on, a very small value depending upon the extent of sparsity that we want to impose. So, for a given type of input data, if the sparsity constant or the sparsity parameter is very low, say for example 0.01, then the number of nodes which will be active in the hidden layer for a given type of input is very small, and most of the hidden layer nodes will be inactive. If we increase this sparsity parameter, that is make the value of rho instead of 0.01, say make it 0.2, then the number of nodes which will be active in the hidden layer for the same input data will be larger than before. So, if the sparsity parameter is 0.01, if the number of nodes which are active is the m, if I make the sparsity parameter to be 0.5, the number of nodes which become active is n, then it is quite obvious that n will be more greater than m. So, depending upon the sparsity constant or the value of the sparsity parameter that you specify, you are controlling the number of nodes which will be active in the hidden layer. Okay. So, in the process, the network learns a generalizable encoding decoding scheme. It just not simply memorize the input data for reproduction later by the decoder part. So, today or in this lecture, what we are going to discuss about a denoising autoencoder, and we will also discuss about contractive autoencoder, and later on we will try to see some applications of the autoencoder. So, what is denoising autoencoder? So, as we said that an autoencoder learns a generalizable encoding decoding scheme. It does not simply memorize the input data. And in the earlier case, in earlier two types of autoencoders, in case of undercomplete autoencoder, that was done by restricting the number of nodes in the input layer. In case of sparse autoencoder, it was achieved, that is generalizable learning or encoding decoding scheme was achieved by introducing a sparsity constant for the activation function of the hidden layer nodes. In case of denoising autoencoder, what you do is, while training the neural network, the training data is corrupted or it is perturbed, and the perturbed data is fed to the input of the autoencoder. Whereas, we expect that the output of the autoencoder should be the original unperturbed data. So, now for training purpose, because you are feeding the input data which is a perturbed one or a noisy one, whereas I want the output data to be the original input or the original data, training data. So now there is a difference between input and output. The input is perturbed data or noisy data, output is original data. So because there is difference between input and output, this autoencoder or denoising autoencoder cannot simply memorize the input data, because while learning, the input data and output data, they are different. The input is the perturbed one, the output is the original one. So it cannot simply memorize the input data. Rather, in this training, while being trained, what the autoencoder learns is a vector field. So it's a vector field that will map the input data towards a low dimensional manifold. So we'll come to what's a low dimensional manifold a bit later. So the training process is something like this. So here what I have shown is, say, this is my autoencoder, where this portion is the encoder part, and if my input vector is some x, then what this encoder does is it implements an encoding function which is say fx. And this part is decoder part. The decoder part decodes this encoded data. So if I put that this function is g, so decoder performs g of fx, and that is my reconstructed data x hat. Right. So in case of this denoising autoencoder, what we are doing is, suppose my original input data or original training data is x, I am adding noise to it or perturbing this input data by a noise process or by a perturbation process to get a noisy data which is x tilde. And this x tilde is fed to the input of the autoencoder. And what I want at the output is this x hat, where I want that this x hat should be this original x, not x tilde. That means during this backpropagation learning, the loss function that I want to minimize is not x tilde x hat, but the loss function that I want to minimize is what is Lx x hat, where x is the original data and x hat is the reconstructed data, or reconstructed x, which is x hat encoded then decoded. So I want that x hat should be equal to g of f of x tilde, where x tilde is the corrupt data or the perturbed data, and I expect that this reconstructed data should be same as my original data x. So the loss function we are minimizing is Lx x hat, where this Lx x hat can be a squared error loss, but that is what we want to minimize. So this is what this denoising autoencoder does. And we have said that while doing so, the denoising autoencoder learns a vector field that maps an input data to a point on a low dimensional manifold. So let us see what is a manifold. Now before coming to this figure, just in simple term, so in any particular residential area, whenever we try to give the address of a building which is on a road, say for example, you name any road, and we give a building number on that particular road. Say a road may be Bidhan Sharoni, and we are simply specifying say 51 Bidhan Sharoni. So the moment you say 51 Bidhan Sharoni, a person reaching Bidhan Sharoni, that particular road, can identify where that 51 Bidhan Sharoni is. So this address that you are giving is a one dimensional address, right? on the road, you move in one direction, come to the building which is number 51. So, 51 Vidhan Shavani uniquely identifies your building on the road. So, this is an one dimensional address. But the building is not an one dimensional in a one dimensional space. The building is actually in a two dimensional space. And to be more specific, the building is in a three dimensional space, because the surface on which we are residing, this surface is part of a sphere. Our earth is nothing but spherical approximately. So, this surface is in 3D. But mostly we approximate that in 2D, because in a very smaller region this can be considered to be a 2D surface. But again, so every building or every place on this surface actually has a two dimensional address. I should specify the latitude, longitude. But instead of doing that, I am simply giving the building number on a road, which is a one dimensional address. So, that is what is a manifold representation. A manifold is actually a very dense space region embedded in a high dimensional space, wherein most of the input data, most of the sensible data resides. So, let us take another example with the set of these images that we have shown. Suppose I want to create an image of dimension m by n. So, as we told in our previous lectures, that an image is nothing but a vector in an m into n dimensional space. Okay. So, there are large number of vectors in that m into n dimensional space. So, if I try to generate any image in that m into n dimensional space by choosing every pixel in that m by n image at random, you find that in majority of the cases or in most of the cases, the kind of image that will be generated is this kind of image, as we are creating every pixel in the image at random. So, in the majority or most of the cases, the kind of image that will be generated is this, and the kind of image like this or the kind of image like this, getting such a type of image by this random selection of pixel values is almost negligible. It may be or may not even be 0.00001%, which clearly says that I have an image space which is m into n dimensional image space, where every possible image of size m into n, m by n is a point. If I choose a point at random, it is very likely that an image I will choose is this. It is very, very unlikely that I will get an image like this. So, that clearly shows that most of the space or most of the volume in that m into n dimensional space represents images of this form, not of this form. Or a sensible image or a set of sensible images like this occupies a very dense low dimensional space, which is embedded in the high dimensional space, which is m into n dimensional space. And this low dimensional space, which is very dense, wherein most of the input data or sensible images in this case they reside, this is what is manifold. Okay. So, in case of autoencoder, when we are representing input data in a compressed domain representation, this compressed domain representation is nothing but a set of points on such manifolds, right. So, given this, now let us see that what is this manifold learning. So, as we have said that for training this denoising autoencoder, I am feeding a data, I am using a training data x. It is quite likely that this training data x will belong to a manifold or it will be taken from a manifold. then I am disturbing this data or perturbing this data to make it data x tilde, which is the perturbed data. So, in this case through a perturbation process or noisy process. So, this data x is perturbed to x tilde, and using this I am training the autoencoder, and what the autoencoder does is, while training, my autoencoder output is, as we have said before, g of f of x tilde, and I want that this g of x tilde should be my x, not x tilde. So, while training by this gradient descent procedure or backpropagation learning, effectively the autoencoder learns a vector field. The vector field is that given any point over here, the autoencoder will try to move this data in a direction which is our nearest point on this manifold. So, this reconstructed x minus my original x, that is what is the vector field. So, over here this vector field or vector field is represented by arrows which are in green color. So, I have vector fields like this over here. So, if I give any training vector somewhere over here, as the vector field is in this direction and it is moving towards the manifold. So, this data which is given over here will ultimately converge or ultimately be represented by a point on this particular manifold, which may be nearest to this input data that was given. This is what is known as manifold learning. So, the advantage of denoising autoencoder that we have just seen is that it prevents the autoencoder from simply memorizing the input data, because for training, the training pair, the input and output data is different. But in the process of training, the autoencoder learns a vector field which helps the autoencoder to move any point in space to a point, a nearest point in on the manifold. Of course, this is possible in a space where the autoencoder has observed some inputs. If I have a point far away from this autoencoder and I did not have any data, any training data over here, in that case my reconstruction error becomes quite large, and it is quite possible that this point will not be converged to a point on the manifold, but this point may go in the other direction as well. So, in the region where the autoencoder has seen some training data, it learns a vector field. In the region, of course, where the autoencoder have not seen a data, it does not have any idea of that particular area and it does not know what to do with that data. So, that is what is manifold learning. And a denoising autoencoder learns a vector field which eventually moves the input data to a point on the manifold. The other kind of autoencoder that we are going to discuss is a contractive autoencoder. The concept of contractive autoencoder is that if the input data is very similar, in that case encoded output of all those input data must also be very similar. So, that is the concept of an autoencoder. So, for similar inputs, the learned encoding or the compressed domain representation should also be very similar. So, this is what is the basic philosophy behind learning of a contractive autoencoder. So, in order to do this, what I have to impose is that the activation or the variation of the activations in the hidden layer, activation of the nodes in the hidden layer, the variation of these activations with respect to input data should be small. That is, if the input data are given two input data, if they are similar, there may be slight variation. the activations in the hidden layer, that should also be very, very similar. Okay. So, by doing this, what such a model or the contractive autoencoder learns is, it learns to contract a neighborhood of input to a small neighborhood of output, right. So, as similar inputs are encoded in a similar way, and when you decode that, the decoder output will also be very, very similar. Okay. So, this ensures that similar inputs at the input or in a small neighborhood at the input will also be contracted to a very small neighborhood at the output. That is what this contractive autoencoder does. And as we are saying, that the kind of regularization that we should impose in case of contractive autoencoder is that the variation of the hidden layer activation should be small with respect to the input data. And that can be imposed by introducing a regularization. Again, here the regularization is on activations, not regularization on the weight values, which is done in case of multilayer perceptron. So, here the regularization is on the activations, and the regularization term can be something like minimization of the Frobenius norm of the Jacobian matrix of the activation functions in the hidden layer. So, what is Frobenius norm? Frobenius norm of a matrix A, as shown over here, if my matrix is A, then Frobenius norm is Aij square, where Aij is the ijth element of the matrix A. Take the sum of all these squared elements over all the elements, that is summation over all I and summation over all j, and take the square root of this. That is what is Frobenius norm. And the regularization term in case of contractive autoencoder can be squared Frobenius norm of the Jacobian matrix. Now, what is the Jacobian matrix? As we have seen that when you have taken gradient of the loss function was a scalar, our weights are vectors, right. So, when you take the gradient of a scalar function with respect to a vector, the gradient becomes a vector. Over here, for every hidden layer node, I have input which is a vector or a data vector. And if I have multiple nodes in the hidden layer, then the activations taken together, they are also vectors. So, if I take the gradient of this vector with respect to input vector, so gradient of scalar with respect to a vector, that becomes a vector. So, gradient of a vector with respect to vector should become a matrix. So, and that is what is Jacobian matrix. So, Jacobian matrix actually captures the variation of different components of the output vector with respect to the input vector. So, the Jacobian matrix in this case is defined this way. Suppose I have nh number of nodes in the hidden layer. So, I will have nh number of activation values, one activation value of every hidden layer node, and my input data vector is say m dimensional. There are m components of the input data vector. So, the Jacobian matrix simply becomes like this: A1H, which is the activation of the first node in the hidden layer for input vector x. So, it is del A1x, A1HX upon del x1, del A1HX upon del x2, and so on. So, the first row actually gives you the gradient of the output of the first node in the hidden layer with respect to the input vector. Second row tells you the gradient of the output of the second node of the in the hidden layer with respect to the input vector x, and so on. Similarly, last row gives you the gradient of the output of the nhth node in the hidden layer with respect to the input vector. And all of them together gives you what is the Jacobian matrix. And my regularization term now becomes a squared Frobenius norm of this Jacobian matrix. So, you find that this del x, a, I, h, x, all of them together are nothing but components of this Jacobian matrix. So, this is what is my regularization term. So, my backpropagation learning algorithm now should try to minimize this along with the data loss that I have, which is L x x hat, right. So, this regularization term ensures that variation of the activations in the hidden layer nodes with respect to the input will be very small, minimum, once the network is learned properly. And that is what is our contractive autoencoder. And as we said that this contractive autoencoder tries to contract a neighborhood of the input data to a small neighborhood of the output data. So, given this, let us now try to see what are some possible applications of such autoencoder. One of the application is what is called inpainting. The inpainting says that if I have an original image where the original image is corrupt in the sense that some region I do not have any information in some region, or the information contained in some of the regions, some smaller regions is totally corrupted. So, you find that because autoencoder learns a salient features of the image, and from the salient features the decoder part can reconstruct the image. So, it is possible that autoencoder will be able to remove such corrupted regions from the input image, which is the inpainting as is shown here. So, here these black regions as shown, these black regions are now the missing regions, and by inpainting you can cover those black regions. So, this is one of the applications where the autoencoder can be successfully applied. The autoencoders can also be applied in abnormality detection. For example, I have a surveillance camera. The purpose is to detect any abnormal event. Say for example, I have a pedestrian road where only the pedestrians are supposed to move. There should not be any car on the pedestrian road. So, when I train the autoencoder, I train the autoencoder with only normal sequences where only the pedestrians are present. And then when I employ this autoencoder in the test sequence, if any car comes on that pedestrian road, because while training the autoencoder has not seen the car, so the car cannot be properly reconstructed by the autoencoder. So, on the output side, if I can identify regions of the image frames where the reconstruction error is very large, as we have said that car cannot be properly represented, cannot be properly reconstructed as car was not seen during training. Pedestrians were seen during training. So, pedestrians will be properly reconstructed, but not the car. So, in that particular region, the reconstruction error where the car is present is very high because it is not properly reconstructed. So, in the output video sequence, whichever region I find that the reconstruction error is very large, I can identify that in those regions we have some abnormal activity taking place. Okay. So, these trained autoencoders can also be used for such abnormality or abnormal activity detection. And as it is obvious from the denoising autoencoder that autoencoder obviously can also be used for filtering purpose, that is removal of the noise. So, there are many such applications where autoencoders can be applied. So, we will talk about other models of the deep learning, other types of neural networks in our subsequent lectures. So, let us stop today. Thank you.